Welcome to all my viewers one last time. This is my last lecture in this course, that is power generating units. I have brought here unit number 5, which is hydraulic turbines and hydropower controls. We have seen so many things about this hydraulic power plant, hydraulic power generation, the component, the safety measures, government influences, environmental concerns, as well as the various working principle of different components. In this slide, we will mostly keep our discussions limited and concise only up to this hydraulic turbines and hydraulic power controls. Hydraulic turbines are the prime movers that convert the energy of the falling water into a rotational mechanical energy and consequently to an electric energy through the use of the generators that are connected to the turbines. Turbines consist of a row of blades that are fixed on a rotating shaft or a plate. The shaft rotates because of the impact of the difference in velocities and pressure of the water striking the blades. Hydraulic turbine can be classified based on different categories. For instance, in axial flow turbines, the direction of water stream is parallel to the axis of the rotation of the blades or shaft, such as Kaplan and propeller turbine. In radial flow turbines, the direction of water stream is perpendicular to the axis of rotation of the blade or the shaft, such as Pelton turbine. In mixed flow turbine, the direction of water flow entering the turbine is different from the direction at which the water leaves the turbine, such as Francis turbine. In cross flow turbine, the water flow passes through the turbine diagonally or across the turbine blades. In these types of turbine, the water flow passes through the runners 2 times, increasing the efficiency of the turbine. Cross flow turbines are utilized at sites with high flow rate and small head. Now, I will give you a brief introduction about the classification of turbine. Just now I have talked, but here let us talk about the major classification of turbine. The main classification depends upon the main type of action of water on the turbine. They are impulse turbine and reaction turbine. Impulse turbine, in this case, in the case of impulse turbine, all the potential energy is converted to kinetic energy in the nozzle. The impulse provided by the jet is used to turn the turbine wheel. The pressure inside the turbine is atmospheric. This type is found suitable when the available potential energy is high and the water available is comparatively low. Now, reaction turbine. In reaction turbine, the available potential energy is progressively converted in the turbine's rotor, and the reaction of the accelerating water causes the turning of the wheel. These are again subdivided into radial flow, mixed flow, axial flow machines. Radial flow machines are found suitable for moderate level of potential energy and medium quantities of flow. The axial machines are suitable for low levels of potential energy and large flow rates. An axial turbine is a turbine in which the flow of the working fluid is parallel to the shaft, as opposed to radial turbines, where the fluid runs around the shaft as in a water mill. An axial turbine has a similar construction as an axial compressor, but it operates in reverse, converting the flow of fluid into rotating mechanical energy. A set of static guide vanes or nozzle vanes accelerates and adds swirl to the fluid and directs it to the next row of turbine blade mounted on the turbine rotor. The wheel and the blades should have access to the blades that are always under the action of free air and must not run fully. Only one face of the blade is active. Both sides regulation of flow and power is easier without significant loss in energy due to changes in the pressure head. Now, let us talk about the important or critical turbine one by one. Pelton turbine. We have seen so many details. Here also we will see some new things about Pelton turbine. Specifically, it is an impulse turbine that we already know. This is the only type used in high head power plant. Wherever head is available is very high, there we go for this type of turbine. This type of turbine was developed and patented by L.A. Pelton in 1889, and all the types of turbine is called by his name to honor him. A sectional view of this horizontal axis Pelton turbine will be shown in a figure in the PPT, which I will share with you all. The main components of this Pelton wheel impulse turbine are the runner with the vanes buckets fixed on the periphery of the same, the nozzle assembly with control sphere and deflector, and the brake nozzle and the casing. Now, let us have a little discussion on the working of Pelton turbine. Nozzles direct forceful high speed streams of water against a series of spoon shaped buckets, which are also known as impulse blades, which are mounted around the outer rim of the drive wheel, also called as runner. As the water jet hits the blades, the direction of water velocity is changed to follow the contour of the blades. The impulse energy of the water jet exerts torque on the bucket and wheel system. Spinning the wheel, the water jet takes a U-turn and exits the outer sides of the bucket, decelerated to a lower velocity. In the process, the water jet's momentum is transferred to the wheel and hence to the turbine. Thus, impulse energy does work on the turbine, and that is why it is called as an impulse turbine. Maximum power and efficiency are achieved when the velocity of the water jet is twice the velocity of the rotating buckets. This is the condition, and when you will study further, you will learn the derivation of this fact also. A very small percentage of water jets original kinetic energy will remain in the water, which causes buckets to be emptied at the same rate it is filled, and thereby allows high pressure input flow to continue uninterrupted and without waste of energy. Typically, two buckets are mounted side by side on the wheel with water jet split into two equal streams. This balances side load forces on the wheel and helps to ensure smooth efficient transfer of momentum from water jet to the turbine wheel. Because water is nearly incompressible, almost all of the available energy is extracted in the first stage of the hydraulic turbine. Therefore, Pelton wheel have only one turbine stage, unlike gas turbine that operates with compressible fluid. Pelton wheel are preferred turbine for hydroelectric plant where water source has relatively high hydraulic head at low flow rates. Now, let us study some advantages associated with Pelton wheel hydraulic turbine. The Pelton wheel turbine is simple in design and also the construction is not complex. The water, which is clean, cannot cause very rapid wear in high speeds. The overall annex inspection are much easier than other turbine. Cavitation is not an ever present danger here, which will be in the case of other turbines. The water hammer effect is not here. The overall efficiency is quite high as compared to reaction turbine, and there is no requirement for a draft tube here. It works on relatively lesser discharge or flow rate. In the hydraulic turbine, it is the most efficient turbine that we use in our hydraulic power plant. The parts assembly of the Pelton wheel turbine is very easy, no complexity here, and the water striking and leaving the runner is approximately at atmospheric pressure. This is a tangential flow turbine. It can move in axial flow or radial flow. Now, there are some disadvantages associated with Pelton turbine. Let us go through them. In a Pelton wheel turbine, the variation in operation head cannot be easily controlled because it works at high heads. The ratio of maximum and minimum operating heads can be even less. The operating head cannot be utilized when the variation in the tail water level is relatively large when compared to the total head. The mechanical efficiency of the Pelton wheel decreases faster compared to the Francis turbine. The size of the runner, generator, powerhouse required is large and not economical if the Pelton turbine is used instead of Francis turbine for the same power generation. Now, different types of efficiencies associated with turbines. Let us have a look at some efficiencies type. Number 1, hydraulic efficiency, number 2, mechanical efficiency, number 3, overall efficiency, and number 4 is volumetric efficiency. I am sure in your future lectures, in your upcoming studies, you all students will study in detail about all these efficiency. Here I will just give you the basic brief introduction about all these efficiencies associated with hydraulic turbines. Number first, we have hydraulic efficiency. It is defined as the ratio of power developed by the runner to the power supplied by the jet at the entrance to the turbine. Mathematically, you can write it as hydraulic efficiency is equal to power developed by the runner divided by power supplied at the inlet of the turbine, and there is a mathematical derivation and mathematical equations also for this, which you have to refer in textbooks of this subject. Now, mechanical efficiency. It is defined as the ratio of power obtained from the shaft of the turbine to the power developed by the runner. These two power differ by the number of mechanical losses such as bearing losses, frictional losses, etc. Then we have volumetric efficiency. The volumetric efficiency is the ratio of the volume of water actually striking the runner to the volume of water supplied by the jet to the turbine. And finally, we have overall efficiency. It is defined as the ratio of power available at the turbine shaft to the power supplied by the water jet, or mathematically you can write overall efficiency as overall efficiency is equal to power available at the turbine shaft divided by power available from the water jet. Now, let us quickly recall about the concept of heads which we have studied through one diagram in the PPT which I will share with you, shows a general layout of hydraulic power plant using an impulse turbine, that is Pelton wheel. In that you can see all the types of head. Gross head, the gross head is difference between the water level at the reservoir and the water level at the tail race. It is denoted by the symbol Hg. Remember, G will be in suffix, capital H and small g in suffix. Net head or effective head. The head available at the inlet of the turbine is known as net or effective head. It is denoted by capital H and it can be given by capital H is equal to capital Hg, that is total head minus head loss due to friction minus head loss due to other factors. So, you can clearly see the difference between the effective head or net head and the total head. The effective head will be always less than the total head, because total head does not include any kind of frictional losses or other losses. The other losses will be also there, but the majority of the losses will take place due to losses in friction, and for that reason you need to know the method, you need to know the formula to calculate head loss due to friction, and head loss due to friction can be calculated by a simple relation which is called as Darcy-Weisbach equation, whose derivation you will study in your UG classes. From that we can calculate head loss due to friction from the relation 4 FLV square upon 2 GD, where L is the length of the penstock, D is the dia of the penstock, V is the velocity of flow in the penstock, H will be the height of the nozzle above the tail race, and F will be the coefficient of friction. Now, having this discussions on impulse turbine, let us go through reaction turbine. In reaction turbine, runner utilizes both potential as well as kinetic energy. As the water flows through the stationary part of the turbine, whole its pressure energy is not transformed to kinetic energy, and when the water flows through the moving parts, there is a change both in pressure and in the direction and velocity of flow of water. As the water gives up its energy to the runner, both its pressure and absolute velocity get reduced. The water which acts on the runner blades is under a pressure above atmospheric, and the runner passages are always completely filled with water. Important reaction turbines that we use are Francis, Kaplan and propeller turbine. Now, quickly let us go through Francis turbine. The Francis turbine operates under medium heads and also requires medium quantity of water. It is employed in medium head range power plant. This type of turbine covers a wide range of heads. The head acting on the turbine is partly transformed into kinetic energy and the rest remains at pressure head. There will be a difference of pressure between the guide vanes and the runner, which is called as the reaction pressure and is responsible for the motion of the runner. Now, the main parts of the Francis turbines are again penstock, then penstock we have already seen, penstock, then spiral scroll casing, then guide vanes, then governing mechanism, then runner and runner blades, then draft tube. Now, we will see the advantages and disadvantages of Francis turbine with respect to Pelton turbine. Let us first go through the advantages. The Francis turbine claims following advantages over Pelton wheel. In Francis turbine, the variation in operating head can be more easily controlled. It is difficult to control Pelton turbine than Francis turbine. In Francis turbine, the ratio of maximum and minimum operating heads can be even 2. The operating head can be utilized even when the variation in the tail water level is relatively large when compared to the total head. The mechanical efficiency of Pelton wheel decreases faster with wear than Francis turbine. The size of the runner, generator and powerhouse required is small and economical if the Francis turbine is used instead of Pelton wheel. Now, there will be some disadvantages too. As compared with Pelton wheel, the Francis turbine will have some disadvantages. Let us go through that. Water which is not clean can cause very rapid wear in high head Francis turbine. The overall inspection is much more difficult comparatively. The water hammer effect is more troublesome with Francis turbine. If the Francis turbine runs below 50% head for a longer period, it will not only lose its efficiency, but also the cavitation danger will become more seriously. Therefore, we go for some more practically used turbine, that is called as axial flow reaction turbine. It will remove the drawbacks which Francis turbine has compared to Pelton wheel. It has been observed that with increasing specific speed at flow, the flow tends to be axial. If water flows parallel to the axis of the rotation of the shaft, the turbine is known as axial flow turbine. The shaft of an axial flow reaction turbine is vertical. The lower end of shaft is made larger, which is known as hub or boss. The vanes are fixed on the hub and it acts as a runner for axial flow turbines. Now, quickly take a look at propeller and Kaplan turbines. Two important types of axial flow reaction turbine are, first one will be your propeller turbine and the second one will be your Kaplan turbine. In these turbines, all parts such as spiral casing, stay vanes, guide vanes, control vanes and draft tube are similar to mixed flow turbine in design. The water enters the runner in an axial direction and during the process of energy transfer, it travels across the blade passage in axial direction and leaves axially. The pressure at the inlet of the blades is larger than pressure at the exit of the blades. Energy transfer is mainly due to the reaction effect, that is change in magnitude of relative velocity across blades. Now, let us take a look at some aspects of design of this axial flow reaction turbine. In axial flow turbine, the number of blades are fewer and hence the loading on the blade is larger. Smaller contact area causes less frictional losses compared to mixed flow turbines, but the peripheral speed of the turbine is larger. Now, another factor is that axial flow rotors do not have a rim at the outer end like the Francis rotors, but the blades are enclosed in a cylindrical casing. The clearance between the blades and the cylindrical casing is small, hence the flow past the blades can be considered two dimensional. The water coming out from the guide vanes undergoes a whirl which is assumed to satisfy the law of free vortex. The hub and the smallest at the outer end of the blade, hence the blade is twisted along its axis. Now, quickly take a look at the propeller turbine. The propeller turbine is a reaction turbine used for heads between 4 meter and 80 meter. It is purely axial flow device providing the largest possible flow area that will utilize a large volume of water and still obtain flow velocities which are not too large. The propeller turbine consists of an axial flow runner with 4 to 6 or at the most 10 blades of airfoil shape. The runner is generally horizontal, that is the shaft will be vertical. The blades resemble the propeller of a ship, that is why it is named propeller turbine. In the propeller turbine, as in Francis turbine, the runner blades are fixed and non-adjustable. The spiral casing and guide blade are similar to those in Francis turbine. Now, quickly take a look at Kaplan turbine. A propeller turbine is quite suitable when the load on the turbine remains constant. At part load, its efficiency is very low since the blades are fixed. The water enters with shock and eddies are formed which reduces the efficiency. This defect of the propeller turbine is removed in Kaplan turbine. What will happen in Kaplan turbine? In a Kaplan turbine, the runner blades are adjustable and can be rotated about pivots fixed to the boss of the runner. The Kaplan turbine has purely axial flow. Usually, it will have 4 to 6 blades having no outside rims. The blades are adjusted automatically by servo mechanism, so that at all the loads the flow enters through them without shock. Thus, a high frequency is maintained even at part load. The servo meter cylinder is usually accommodated in the hub. Kaplan is also known as variable pitch propeller turbine, since the pitch of the turbine can be changed because of adjustable vanes. The Kaplan turbine behaves like a propeller turbine at full load conditions. Now, after seeing the various types of turbine, that is impulse turbine also we have seen, reaction turbine also we have seen in detail about Pelton, we have seen in detail about Francis, Kaplan, then mixed flow, axial flow, all that we have seen. Now comes the second part of this unit, that is turbine control. It is the speed oblique load control of the turbine and governor. It is the main controller in which the governor adjusts the flow of the water through the turbine to balance the input power with the load. In case of small plants in the range of microhydel, that is up to 100 kilowatt in size, load control is also used, where excess load is diverted to dummy load to maintain constant speed. With an isolated system, the governor controls the frequency. In interconnected system, the governor may be used to regulate the unit load and may contribute to the system frequency control. Now, in the slide which I will share with you, that will show you a figure that will represent different types of control applicable to turbines. Here it was not feasible for me to show you the figures or to explain, therefore, I will share it the PPT. Governor functions are as follow. Few functions I have given. Runner water admission. The admission of water to the runner in accordance with the load demand is controlled by needle adjusted nozzle in impulse turbine and by guide vanes in reaction turbine. All these form of control employ oil servo mechanisms. Rapid fluctuations of flow may cause disastrous water hammer fractures. Minimum governor closing times in reaction turbine are fixed and gradual closure or opening is provided to avoid water hammer pressure rise or drop limits. In impulse turbine, deflector plates take the jet of the runner instantaneously, the jet being cut off gradually afterwards. In Kaplan machine, what happens is the runner blades are variable in pitch and are adjusted simultaneously with the guide vanes by means of an oil servo motor within the runner hub. In semi Kaplan turbine, what happens? The fixed guide vanes opening is adjusted to water requirements for load. Now, let us have a look on types of turbine governor. We have number 1 speed and power control section, then we have mechanical or hydraulic actuator. Mechanical or hydraulic actuator is for control of wicket gate or nozzle control for all types of turbine and blade angle control for Kaplan turbine in addition to wicket gate control. Size and type of governor is based on the capacity of the actuator. Now, in speed and power control, we have 3 types of governor for speed and power control of hydraulic turbine. They are mainly in use. They are mechanical governor, analog electronic governor and digital electronic governor. We will see all 3 in brief. First one, we have mechanical governor. Mechanical governor were universally used in hydropower plant up to 1965 or so. In these types of governor, a synchronous motor is run by a shaft. Permanent generator senses the speed and fly balls fixed to the sleeves control the pressure oil system for servo motor control. Speed sensing and control section are physically linked to mechanism hydraulic actuator. Performance adjustment of signals for able operation and permanent speed drop, temporary speed drop and dash drop of about 7 to 14 times are by adjusting mechanical linkages. Now, we have second type of governor control that we call it as analog electronic governor. In electronic governor, hydraulic actuators speed sensing is by speed signal generators, that is also referred to as SSG. The signal is converted to propagation voltage signal and amplified in a magnetic amplifier. Electronic hydraulic transducer converts proportional signal to release proportional pressure oil for servo motor operation. Feedback control is again by mechanical linkages. Control linkages, that is feedback, are mostly mechanical. Now, we have last type of this governor called as digital electronic governor. These are mostly speed sensing and its processing is digital. PID digital speed control can be combined with unit and plant control functions. All the linkages are electric. It is least expensive. Speed sensing is by digital signal, that is proximity switches etc. Feedback control, that is restoring mechanism, is by electric signal. So, may it be any type of governor, the basic function is to control the regulator of the flow through the turbine. So, may it be mechanical, may it be electrical, may it be electronics, the basic function is the same. Now, let us talk about lubrication system. The lubrication system includes the facilities required for lubricating both the turbine and the generator units. In most cases, the generator lubrication system is self-contained and therefore does not require auxiliary pumps. However, large machines may have bearing lift pumps for use during starting. Some high speed generators use pump for recirculating the lubricant after the machine is running. Oil is circulated through those oil coolers by circulating oil pumps. Automatic control scheme must consider for operating requirements of the lubrication system during starting, running and shutdown. Now, let us have a look on generator control system. This is the excitation control of synchronous generator. The excitation is an integral part of the synchronous generator which is used to regulate the operation of the generator. The main function of the excitation system of a synchronous generator, I have listed it out. Number first, voltage control in the case of isolated operation and synchronizing. Number second, reactive power or power factor control in case of interconnected operation. Now, let us have a look at generator cooling systems. Generator cooling involves air circulation by rotor fans. Generators are usually ventilated on the same closed system in which the same air is continuously recirculated and passes through the water cooling units. The water supply for both oil and air coolers can be readily be drawn from the turbine casing through the reducing valves and strainers, so that it flows automatically when the main inlet valves are open. When water head is high, it is more economical to pump from the tail race or draft tube. Each turbine may have their own pump, generally with one standby common to all units. In small hydro cooling, water is sometimes pumped from underground by submerging pump to avoid elaborate treatment plant for cleaning water. Now, let us talk about braking and jacking system. Braking assists big machine to minimize bearing wear by restricting protected slow running before stopping. Impulse turbine have separate reverse acting jet controlled by independent oil servo motors. When remotely controlled, these jets must be cut off when the machine has stopped to prevent counter rotation occurring. The heavier vertical machines require more powerful brakes in form of oil jacks under the generator rotor, which presses friction pads against special rim or the pressure being applied through air or oil reservoir. The same brakes are employed as jack for lifting the rotor, for withdrawing the thrust pads and to assist in other dismantling operation. In addition, these jacks are sometimes used to lift the rotor before starting in order to flood the thrust bearing pads. So, this was all about lecture number 5, that is turbine units and its control. In this unit, we have seen the various types of turbine in detail. We have seen the classification of hydraulic turbine. Impulse reaction was the main classification. Then we have seen further Pelton, Francis, Kaplan. We have seen the basic working principle, the mechanism of working, the construction mechanism with the help of the PPT, which I will share with you. In that, I will show with the help of diagrammatic representation the construction of all these types of turbine. After turbine, we have seen the control units in detail. In that, we have seen that control units was mainly divided into 3 parts: mechanical, electrical and electronic, each having different sets of operation, but the basic working principle was same, to control the flow rate of mechanism. Then at last, we have seen this lifting and jacking mechanism, we have seen the cooling mechanism, and then we have seen the how to keep the all the systems well under control. So, this was it in my unit number 5. I hope this session was informative, and this session will act as a basic lecture, basic information for all the students who are going to pursue engineering degree in the field of mechanical engineering as well as some other relevant courses. So, go through all my 5 video units. In that, you can find the details about power generating units, you can find a lot of information about hydroelectric power plant. So, this was it from my side. Thank you all for listening to me so patiently. Thank you once again. Thank you very much.